Void safety. This is the end of null pointer dereferencing, and in this part 3, we're going to see the type rules that are a key part of the void safety mechanism. I'm assuming that you've seen parts 1 and 2 of this video series, which are at the references at the URLs listed. We know already that for any type T, there are two variants. There is attached T and detachable T. So for any variable, you can declare it as just being of type T, as for X here, or you can declare it as being of type detachable T. In fact, in the first case, you can write attached T, but you don't have to use the keyword attached here. This is the default. What is important semantically is that as soon as you declare X as being of type attached T, implicitly or explicitly, then there's a guarantee that it will never be void. So you don't have the problem of null pointer dereferencing anymore. Why, by the way, is attached the default? Why don't we have to write attached? It could be the reverse, but in fact it turns out that in practice you will want most of your variables to be attached. For model objects, that is to say for objects in your program that represent concepts on the outside world, bank accounts, person, planes, whatever, there's no notion of a void bank account, well, except in the sense of not having any money, but the object usually is there. And void is not useful for that kind of example. Void is useful essentially to terminate linked structures. We saw this example in the second video where we have a linked list, and at the end of the list, of course, we're going to put a void. This is the standard way of terminating a linked structure. So the basic constraint is that a declaration such as this one is a guarantee that at runtime X will never be void. But that's, of course, the easy part. You can always hand wave and declare X as attached. You will expect then that guarantee that the values of X at runtime will be references that are never going to be void. Let's go back to our example. Remember that we had something that compiled, but as soon as we removed the test for X for P not equal to void, then of course it is not going to compile again because we are trying to compile a program where the target of the object call might be void. The message here is very precise. So if we uncomment the create P, then it's going to work, it's going to compile. Now let's assume that we have in that class another attribute, or another element, in this case an attribute of type person. It seems pretty harmless, right? I'm declaring a new variable Q of type person, and Q is an attribute, meaning it's going to correspond to a field of every instance of the class. So it should compile, should it? Well, no, it's not. It's not going to compile, and the compiler tells us that the variable is not properly set. Well, what does this mean? We're going to understand what this means by looking at what it takes for the compiler to give us that guarantee, that contract, if you like, that whatever happens to X at runtime, it will not be void. In order to achieve this guarantee, there are two things that you must do. You must obey rules on variable initialization and rules on variable assignment and argument passing. Let's start with the second. Let's start with the argument passing and assignment. First, the assignment. If I have an assignment X receives Y, and for example, X is declared of type T, meaning attached T, then Y must also be attached. So you can assign attached to detachable. That's not a problem, of course. If X were declared of type detachable of T, then of course we can assign something to it that could be void. But if X is not detachable, then we must have y which is attached. Now there's a little subtlety here because I didn't write must be of an attached type. I said must be attached because if there's some reason, some clear reason to be sure that even though y might itself be of a detachable type, it will be attached at runtime whenever this instruction is executed, then it's going to be okay, and that's going to be part of our last mechanisms in the next video of this series. But this is the basic rule. If the target is attached, you can only assign an attached to it, and of course the same rule governs argument passing. So x, instead of being a variable, could be an argument, a formal argument of a routine, and if we pass y to it as actual argument, then y must be attached if x is of an attached type. So that's the first rule. It's the attachment conservation rule. It takes care of what happens to variables later in their lives. But of course, variables are first initialized. And here we have a problem. If we take standard Eiffel initialization rules, they are based on the type of a variable. So for example, if the type of is integer or real, the variable will be initialized to 0. If it's a Boolean, it will be initialized to false. If it's a character, it will be initialized to the null character. There's a rule for expanded types, meaning that they must have a default create from class any, which actually serves as a creation procedure to make sure that they are all initialized. But now we have this problem that a reference is in pre-void safe Eiffel and still in today's Eiffel for detachable references. It's initialized, of course, to void. There's nothing better that we can think of as the default value for a reference. But of course, this is also the worst possible initialization in the case of an attached variable for the reference associated with that variable. So we must do something about this. And the something is that at any place where it is accessed, a variable must be properly set. What does it mean to be properly set? Well, it means that it has been initialized. So either it's of one of those types for which there's a default initialization, in which case we don't have a problem, or if it's a reference, it must have been explicitly set. In particular, if it's an attached reference, it must have been properly set. And of course, because of the rules on assignment that we saw a moment ago, this means it must have been given a value that is not void. And so how do we initialize variables? Well, for a local variable, that's the first case that we saw in our example, it's properly set at the beginning of the routine sets it. So here, if we go back to our original example, we had a local variable p, and before we access it, it's been created in the correct version of this code. Now for an attribute, well, an attribute is going to start its life at the end of creation procedures, of constructions of the class. And so the reason why this code does not compile is that the variable q is not properly set. And why is this bad? Well, we could have another feature in the class, in this class application, that tries to use q, and the first time it tries to use q, because q has not been initialized at the end of the creation procedure, it's going to be void, which of course is not permissible. So the other thing that we should do in this example, in order to make it valid, is to create q, and now it's going to compile without any problem. So these are the basic rules. Variables must be properly set, and it means for an attribute that it's properly set at the end of every creation procedure, and for a local variable, it means that it's set towards the beginning of the routine in which it appears. So we now have an almost complete picture of the void safety mechanism. There are two ways to make sure that targets of calls are always non-void, and we've seen a little bit of both. In this lecture, in this segment, we've seen the notion of attached type. So this is where the type system helps us, and we've started to see in the previous lecture how we can, for detachable targets, guarantee that the target is not void. And we saw the first of these patterns by using the object test. This is a special case of a more general situation in which it's clear from the context and the compiler can guarantee that the target of a call will be attached, will not be void. And the general notion is that of a certified attachment pattern. We have seen one cap or certified attachment pattern, and in the next part, in the next segment of this video series, we will complete our understanding of the Eiffel void safety mechanism by seeing the remaining very simple caps.